At 0:30 hours on September 26, 1983, at the Serpukhov-15 early warning facility south of Moscow, a newly deployed satellite surveillance system began reporting ballistic missile launches from the United States. The system detected first one launch, then 5. Confidence levels were high. Alert protocols activated. The data was not the product of computer malfunction or corrupted processing. The satellites themselves, the raw sensor arrays in orbit, were generating the signals. The system was performing precisely as its design specified. This system had been engineered under a premise that its pattern recognition model could discriminate real missile launches from false signatures through infrared characteristics, trajectory analysis, and correlated sensor data. The model had been validated against test scenarios and historical launch profiles. It had been certified operational, yet on this night, the premise collapsed. The model reported what its algorithms interpreted as launches because the physical conditions present, atmospheric reflectance patterns, orbital geometry, ground-based thermal sources, produced sensor data indistinguishable from the training data representing actual threats. The model was correct within its own logic. The model's premise was wrong. The decision architecture placed a human operator between algorithmic output and launch authority. That operator, trained to trust system confidence indicators, faced a choice: believe the model or reject data the system classified as high-probability threat. The system had been designed to reduce uncertainty. Instead, it generated a decision problem for which no procedure existed. How can a validated model produce operationally certain output while being structurally incapable of distinguishing the scenario it was designed to detect? The Oko satellite constellation represented the Soviet Union's most advanced orbital early warning capability in 1983. Unlike ground-based radar systems that detected missiles only after they cleared the horizon, satellites positioned in highly elliptical Molniya orbits could observe launch sites directly. The operational advantage was temporal. Satellite detection could provide 15 to 20 additional minutes of warning compared to radar alone. Those minutes represented the difference between assured retaliation and strategic vulnerability. The system was not a technical luxury, it was a cornerstone of strategic stability. The satellites employed infrared sensors operating in specific spectral bands optimized for detecting the thermal signature of rocket exhaust plumes. During launch, solid and liquid propellant combustion produces intense heat, temperatures exceeding 2,000 degrees Celsius, releasing infrared radiation across multiple wavelengths. The sensors were calibrated to detect these emissions against the baseline infrared background of Earth's atmosphere and surface. The physics was straightforward. Missile launches produce uniquely intense, short-duration thermal events. Detect the thermal spike, correlate its trajectory with ballistic flight characteristics, and classify the event as a launch. The classification algorithm that processed sensor data operated on pattern recognition principles. It had been trained using data from known Soviet missile tests, intelligence on U.S. launch facilities, and atmospheric models representing expected operational conditions. The algorithm evaluated multiple parameters: infrared intensity, spectral distribution, duration, spatial extent, and trajectory consistency. Each detected event received a confidence score reflecting how closely its characteristics matched the training data's launch profiles. High confidence meant strong pattern match. Low confidence meant ambiguous data. The threshold for triggering alerts was calibrated to ensure detection of actual launches while minimizing false positives. This calibration rested on an implicit assumption that the training data comprehensively represented the range of conditions the system would encounter operationally. Test launches occurred during daylight and darkness, clear weather and cloud cover, summer and winter. The model learned to recognize launches under these varied but controlled conditions. What the model did not learn, because the training data could not include it, was how to distinguish launch signatures from naturally occurring phenomena that had never been observed during testing, but could produce similar infrared patterns under specific, rare atmospheric and orbital geometry combinations. The design philosophy prioritized sensitivity over specificity. In strategic terms, failing to detect a real launch, a false negative, risked nuclear annihilation. Reporting a false launch, a false positive, risked political crisis and potential accidental escalation, but preserved the possibility of correction through human judgment and verification procedures. The system was intentionally biased toward detection, better to alert on ambiguous data than miss a real threat. This bias was rational given the asymmetric consequences of error types. It was also the source of structural fragility. The interface between satellite sensors and ground control operators was mediated entirely through processed information. Operators at Serpukhov-15 did not receive raw infrared telemetry showing sensor voltages and spectral intensities. They received threat assessments, alerts indicating detected launches, confidence scores, estimated launch locations, projected trajectories. The information architecture was hierarchical. Satellites collected data. Algorithms processed data into classifications. Classifications triggered alerts. Operators received alerts and executed protocols. At no point in this chain did operators have access to the underlying sensor data that would allow independent verification of the algorithm's interpretation. This architecture reflected a deliberate design choice. Raw sensor data is ambiguous, noisy, and requires specialized interpretation. Training every duty officer to analyze infrared spectroscopy was impractical. Centralizing classification in automated systems ensured consistency, speed, and ostensibly reliability. The algorithm represented consolidated expertise. Operators represented execution. The model was intended to eliminate human uncertainty from the detection process. It succeeded in eliminating human access to the information necessary to question the model's output. The validation process for the OKO system followed standard aerospace testing protocols. Hardware underwent environmental testing to ensure sensors could survive launch, radiation exposure, thermal cycling, and vacuum conditions. Software underwent verification testing to ensure algorithms produced correct classifications when presented with test data matching known launch profiles. System integration testing verified that satellite telemetry correctly transmitted to ground stations and that alerts generated appropriately. The system passed all tests. It was declared operational. What validation could not, test was the algorithm's behavior when confronted with environmental conditions, not represented in the test data. Validation tests what is known and anticipated. It cannot test what is unknown and unanticipated. The atmospheric physics that would produce false positives on September 26, 1983, had never been replicated in testing because those specific conditions, solar angle relative to satellite orbit, cloud altitude and composition, ground thermal source distribution, represented an edge case the test designers had not considered credible or had not encountered during the finite test campaign. The model's training data included missile launches. It included clear skies, cloudy skies, day and night. It did not include every possible combination of solar illumination angle, cloud top altitude, ice crystal structure, surface reflectivity, and orbital viewing geometry. The space of possible atmospheric conditions is effectively infinite. The test data space was finite. The premise that the tested conditions were representative of all operationally relevant conditions was statistically unfounded. The model could only recognize what it had been trained to recognize. Everything else was undefined behavior. Infrared radiation from sunlight reflecting off high-altitude clouds under certain geometric conditions can produce sensor readings similar to those from rocket exhaust plumes. The specific wavelengths, intensities, and durations depend on cloud composition, solar angle, satellite viewing angle, and atmospheric transmission characteristics. Under most conditions, these signatures are readily distinguishable from launches. The infrared intensity is lower, the spatial extent is larger, the duration is longer, the spectral distribution differs. The algorithm had learned these distinctions from training data. But under specific, rare conditions, when sunlight strikes high-altitude cirrus clouds at grazing angles, when ice crystals exhibit particular orientations, when the satellite's viewing geometry aligns such that reflected infrared concentrates in the sensor's field of view, the resulting signature can match launch profiles within the algorithm's tolerance thresholds. The physics is well understood in retrospect. It was not anticipated during system design. The model classified these atmospheric artifacts as launches because, within its learned parameter space, they were indistinguishable from launches. The operators at Serpukhov-15 were trained to trust the system. Training emphasized that the Oko constellation represented the most advanced detection capability available. Operators learned the alert protocols, what actions to take at each confidence level, how to communicate alerts to higher command authority, what verification procedures to attempt within available timeframes. Training did not emphasize skepticism toward high-confidence alerts from a brand-new system. The institutional culture reinforced deference to technology. The satellite system was sophisticated, expensive, rigorously tested. Duty officers were junior personnel executing procedures. The implicit authority hierarchy was clear. The operational context in September 1983 further constrained operator discretion. Geopolitical tension between the United States and Soviet Union was elevated. NATO had conducted Able Archer exercises earlier in the year, exercises that simulated nuclear release procedures and that Soviet intelligence interpreted as potential cover for actual attack preparation. On September 1, Korean Airlines Flight 007 had been shot down after straying into Soviet airspace, killing all aboard and escalating international tensions. The strategic environment was characterized by mutual suspicion and hair-trigger alertness. In this context, dismissing high-confidence alerts from a strategic early warning system was not merely procedurally questionable, it was potentially catastrophic. The system's design premise was that validated algorithms could reliably distinguish signal from noise, threat from false alarm, reality from artifact. This premise required that operational environmental conditions fall within the boundaries of test data variability. It required that training data comprehensively sampled the operational environment's relevant parameter space. It required that edge cases, rare combinations of conditions producing ambiguous signatures, were either included in testing or were sufficiently improbable to neglect. None of these requirements was guaranteed. All were assumed. The assumption that testing ensures operational reliability is common across complex engineered systems. It is also frequently wrong. Testing validates performance under anticipated conditions. Operational environments generate unanticipated conditions. The gap between anticipated and actual is where failures emerge. In safety-critical systems, this gap is managed through multiple layers of verification, redundancy, and human oversight. The Oko system's design compressed verification time to minutes, eliminated redundant independent confirmation mechanisms, and positioned human oversight after algorithmic classification rather than before it. The design assumed the algorithm would be reliable enough that human judgment would only introduce delay, not value. This assumption encoded a model of human cognition, that human operators, when presented with high-confidence alerts from authoritative systems under time pressure, would recognize false positives through intuition, experience, or independent reasoning unavailable to the algorithm. This model required operators to simultaneously trust the system enough to act quickly and distrust it enough to question its output critically. It required expert judgment without providing the information necessary to form expert judgments. It required skepticism while institutionally discouraging skepticism. The cognitive model was internally contradictory. The contradiction would become operationally explicit at 0:30 on September 26, when the algorithm reported 5 launches with high confidence, and the duty officer had minutes to decide whether the United States had initiated nuclear war with an implausibly small first strike, or the most advanced satellite system in the Soviet arsenal was generating false positives on its first real operational test. The design premise had created a decision architecture that made this moment inevitable. The structural vulnerabilities embedded in the Oko system's design were amplified by a constellation of latent conditions that existed before September 26, 1983. These conditions were not defects in the conventional sense. They were the predictable products of institutional priorities, training doctrine, operational procedures, and the psychological dynamics of human interaction with automated authority. Individually, each condition was defensible. Collectively, they formed a failure architecture that made catastrophic error not merely possible but statistically inevitable given sufficient operational time. The Serpukhov-15 facility operated under Soviet military protocols that emphasized discipline, procedural compliance, and respect for technical authority. Duty officers were selected for reliability, not independent judgment. Training focused on execution speed and accuracy, not critical analysis of system outputs. This was rational within the operational context. Strategic early warning systems exist to provide maximum decision time to political and military leadership. Every second spent questioning an alert is a second subtracted from response options. If the alert is real, hesitation could mean national annihilation. The training doctrine reflected this calculus. Trust the system, execute the procedure, escalate the alert. Do not delay. Do not second guess. Do not introduce human uncertainty into a process optimized for speed. This doctrine created a cognitive trap. Operators were trained to treat high-confidence alerts as reliable. They were not trained to assess whether a high-confidence alert was plausible given strategic context. The distinction is critical. A detection system can report high confidence based solely on pattern matching without evaluating strategic logic. An operator equipped to assess strategic plausibility might recognize that a 5-missile launch from the United States made no sense as a first-strike doctrine. 5 missiles could not neutralize Soviet retaliatory capability. 5 missiles could not achieve strategic surprise. 5 missiles represented either a technical malfunction, a limited test gone wrong, or a provocation, but not a rational opening to nuclear war. This reasoning requires strategic knowledge, situational awareness, and authorization to apply judgment in contradiction to system output. Soviet duty officers at Serpukhov-15 were not trained for this role. They were trained to report what the system reported. The authority hierarchy reinforced procedural compliance. Duty officers were junior personnel. The satellite system represented enormous institutional investment, years of development, and the technical expertise of the Soviet aerospace and defense establishment. Questioning the system meant asserting that one's own judgment, that of a junior officer with limited technical training, was superior to the consolidated expertise encoded in the algorithm. The cultural barrier to such assertion was substantial. Military hierarchies reward deference to authority and punish insubordination. An officer who dismissed a real alert would face catastrophic career consequences and possible criminal prosecution. An officer who escalated a false alert would be following procedure. The incentive structure was asymmetric. False escalation was safe. Independent judgment was dangerous. This asymmetry was compounded by the newness of the OCO system in September 1983. The satellite constellation had only recently achieved full operational capability. Duty officers had limited experience with the system's normal operational behavior. They had not yet developed intuition for what typical alerts looked like, what patterns indicated real threats versus technical anomalies, what sensor behaviors were routine versus suspicious. In mature operational systems, experienced operators develop tacit knowledge, informal expertise about system quirks, typical failure modes, and subtle indicators of data quality issues. This knowledge takes years to accumulate. The OCO system had not been operational long enough for this expertise to develop. Operators were forced to rely entirely on formal training and documented procedures. Both emphasized trust and compliance. The information presented to operators was algorithmically processed and deliberately simplified. The control room display did not show raw infrared sensor voltages, spectral analysis plots, or confidence interval distributions. It showed classified alerts, launch detected, confidence high, estimated location, projected trajectory. This simplification was intentional. Raw data is cognitively overwhelming. Presenting processed classifications allows rapid comprehension and response. But simplification eliminates the peripheral information that expert operators use to assess data quality. An experienced analyst examining raw sensor data might notice anomalies in spectral distribution, unusual intensity fluctuations, or spatial patterns inconsistent with launch physics. An operator viewing only the final classification, launch detected confidence 0.95, has no access to these cues. The interface design optimized for speed at the cost of diagnostic depth. The time pressure inherent in strategic early warning eliminated any realistic possibility of independent verification. Ballistic missiles travel from launch to target in approximately 30 minutes. Satellite detection provides warning, but that warning must be transmitted, processed, evaluated, and escalated through command authority quickly enough to preserve decision options. If the alert is real, every minute spent verifying reduces response time. The decision architecture assumed that verification would occur after escalation, at higher command levels with more resources and authority. The duty officer's role was not to verify but to report promptly. This architecture worked if the algorithm was reliable. If the algorithm generated false positives, the architecture guaranteed that false information would propagate rapidly through the command chain before anyone with sufficient authority and technical capability could assess its validity. The psychological dynamics of human automation interaction further constrained operator discretion. Decades of research in human factors engineering have documented the phenomenon of automation bias, the tendency for human operators to trust automated systems even when those systems provide incorrect information. Automation bias is strongest when systems are perceived as authoritative, when operators lack independent means of verification, when time pressure prevents careful analysis, and when institutional culture reinforces deference to technology. All of these conditions existed at Serpukhov-15. The OCO system was presented as state-of-the-art, technically sophisticated, thoroughly tested. Operators had no independent sensors or data sources for verification. Alert protocols required rapid response. Training and culture emphasized trust. The psychological environment was optimized for uncritical acceptance of system output. This environment was further shaped by the geopolitical context of September 1983. The Cold War was not an abstract strategic competition. It was a lived reality characterized by genuine mutual fear, intelligence failures, provocative incidents, and near-constant military readiness. NATO's Able Archer exercises in November 1983, occurring just weeks after the Serpukhov-15 incident, would bring the United States and Soviet Union as close to accidental nuclear war as they had been since the Cuban Missile Crisis. Soviet intelligence interpreted Able Archer as potential preparation for actual attack. In this environment, dismissing high-confidence alerts seemed not prudent, but reckless. The strategic context made trusting the system feel like the only responsible choice. The duty officer on watch the night of September 26 was Lieutenant Colonel Stanislav Petrov. Petrov's assignment to duty that night was partly circumstantial. As a systems engineer involved in the OCO development program, he possessed technical knowledge of satellite operations and algorithm design that typical duty officers lacked. This knowledge was simultaneously an asset and a liability. It gave him insight into how the system worked and where its limitations might lie. It also gave him awareness that questioning the system meant contradicting his own professional work and the work of colleagues he respected. The psychological burden of such contradiction is substantial. Engineers are trained to trust their designs unless evidence of failure is clear. The evidence on September 26 was not clear. It was ambiguous. The specific conditions Petrov faced that night were a product of this accumulated latent failure structure. He received high-confidence alerts from multiple satellites reporting progressive detections, first 1 launch, then 5. The algorithms reported certainty. The data appeared consistent across sensors. No contradictory information was available. Radar systems had not yet detected incoming missiles, but this was expected. Radar detection would occur later in the missile trajectory. The absence of radar confirmation was not evidence against the alert. It was simply the normal temporal sequence of detection methods. Petrov had minutes to decide whether to escalate the alert to higher command authority. Protocol required escalation. Training required escalation. Institutional expectations required escalation. The system demanded escalation, yet Petrov chose not to escalate immediately. His reasoning was not based on technical evidence that the system was malfunctioning. He had no such evidence. The satellites were functioning normally. The algorithms were executing correctly. There was no hardware failure, no software error, no obvious data corruption. Petrov's reasoning was based on strategic implausibility. 5 missiles made no sense. The United States would not initiate nuclear war with 5 missiles. A real first strike would involve hundreds of missiles launched simultaneously to overwhelm Soviet defenses and destroy retaliatory capability. 5 missiles could not achieve strategic objectives. Therefore, despite high algorithmic confidence, despite correct sensor operation, despite multiple correlated detections, the alert was probably wrong. This reasoning required Petrov to assert his strategic judgment against the system's technical authority. It required him to trust human intuition over algorithmic output in a context where institutional culture, training doctrine, procedural requirements, and career incentives all pushed toward the opposite choice. It required him to take personal responsibility for a decision that, if wrong, could result in Soviet retaliation being delayed until it was no longer possible. The psychological weight of this decision cannot be overstated. Petrov was not choosing between obvious right and wrong. He was choosing between conflicting imperatives when no choice was safe and no information was definitive. The latent conditions that created this impossible choice were not accidents. They were design decisions. The decision to prioritize speed over verification was deliberate. The decision to present operators with classifications rather than raw data was intentional. The decision to train for compliance rather than critical judgment was systematic. The decision to position human oversight after algorithmic processing rather than before it reflected conscious engineering philosophy. Each decision was locally rational. Each decision made sense given the constraints and priorities of strategic early warning system design. Collectively, they created a system architecture in which a false positive would propagate exactly as a true positive would, and in which the only barrier to catastrophic escalation was individual human judgment exercised in defiance of procedure, training, and institutional authority. The irony is profound. The system was designed to eliminate human error from the detection process by automating classification and constraining operator discretion. It succeeded in eliminating the kind of human error that causes delays and inconsistencies. It also eliminated the kind of human judgment that recognizes strategic implausibility and questions algorithmic certainty. The system solved the problem it was designed to solve. In doing so, it created a different problem: how to prevent automated authority from being trusted when it should be questioned, in an operational context that makes questioning both practically difficult and institutionally dangerous. The alignment of these latent conditions, procedural doctrine, training emphasis, information architecture, authority hierarchy, time pressure, psychological bias, geopolitical context, and individual assignment, was not a conspiracy of failures. It was a convergence of ordinary organizational dynamics. Every complex system contains latent vulnerabilities. Most of the time, these vulnerabilities remain dormant because the specific combination of conditions required to activate them does not occur. On September 26, 1983, the conditions converged. The algorithm encountered an environmental edge case not represented in its training data. The operator faced a decision problem for which his training provided no guidance. The institutional structure demanded action that could have initiated nuclear escalation. The only element that prevented escalation was Petrov's willingness to violate protocol based on strategic reasoning he was not formally authorized to apply. This raises a disturbing question about system design. If reliable operation depends on individual operators being willing and able to override procedures in defiance of automation, training, and institutional pressure, then the system's safety margin exists only to the extent that operators possess uncommon judgment and uncommon courage. This is not a robust safety architecture. It is organizational luck masquerading as engineering design. The fact that the system did not fail catastrophically on September 26 was not evidence that the system was well designed. It was evidence that one individual happened to possess the technical knowledge, strategic understanding, and psychological independence necessary to recognize that high confidence does not equal high validity. The next operator might not possess these qualities. The next false positive might propagate without interruption. The physical conditions that produced the false positive alerts on September 26, 1983, were the product of orbital mechanics, atmospheric optics, and solar geometry, converging in a configuration the OCO system's classification algorithm had never encountered during training. The satellites were not malfunctioning. The sensors were detecting real infrared emissions from real physical sources. The algorithm was executing its pattern-matching logic without error. The classification output, launch detected, high confidence, was correct according to the model's learned parameters. What was wrong was not the system's operation, but the premise that similar infrared signatures always indicate similar physical causes. The OCO satellites occupied highly elliptical Molniya orbits designed to maximize viewing time over the northern hemisphere where U.S. ICBM launch sites are concentrated. At apogee, the highest point in the orbit, satellites move slowly relative to ground features, allowing extended observation periods. The orbital parameters placed satellites approximately 40,000 kilometers above Earth's surface at apogee, with inclination angles that provided coverage of North American missile fields. This geometry was optimized for strategic warning. It also created specific viewing angles relative to Earth's atmosphere and the Sun's position that could, under certain conditions, produce optical effects not anticipated during system design. On the night of September 26, the orbital positions of multiple OCO satellites, the Sun's angle relative to Earth, and the presence of high-altitude cloud formations over the northern Pacific created conditions in which sunlight reflecting off ice crystal clouds produced infrared signatures that matched the algorithm's launch classification criteria. The physics involved is well understood in atmospheric optics but was not incorporated into the OCO training data because the specific combination of orbital geometry, solar angle, cloud altitude, and ice crystal structure required to produce launch-like signatures had not been identified as a credible false positive scenario during system development. High-altitude cirrus clouds, thin clouds composed of ice crystals at altitudes between 9 and 12 kilometers, can reflect and scatter sunlight in complex ways depending on ice crystal shape, orientation, and size distribution. When sunlight strikes these clouds at grazing angles near sunrise or sunset, and when the viewing geometry positions an observer at specific angles relative to the reflection, the result can be intense, localized infrared emissions in the spectral bands the OCO sensors were designed to detect. The emissions are not thermal in the sense of blackbody radiation from hot gases. They are reflective, solar infrared reflected, and concentrated by ice crystal optics. But to the satellite sensor, both emission types produce similar detector responses within certain wavelength ranges. The algorithm had been trained to distinguish launches from clouds based on temporal characteristics, spatial extent, and spectral distribution. Real launches produce rapidly evolving signatures. The thermal plume expands as the rocket accelerates, the infrared intensity increases during powered flight, and decreases after burnout. The spatial pattern follows ballistic trajectory geometry. Clouds produce relatively static signatures. They move with wind patterns, not ballistic arcs, and their thermal characteristics change slowly. These distinctions are robust under most conditions. They break down when atmospheric and geometric conditions produce transient, localized reflections that mimic launch temporal evolution. On September 26, the satellite's viewing geometry positioned them such that they observed a specific region of high-altitude cirrus clouds over the Pacific during a period when solar angle relative to cloud altitude created strong infrared reflection. As the satellite's orbital motion changed their viewing angle, the reflection intensity varied in a manner that the algorithm interpreted as a launch plume evolving through powered flight phases. The temporal signature, increasing intensity followed by stabilization, matched the training data's launch profiles. The spatial extent, concentrated emission covering several kilometers, was consistent with early-phase missile plumes. The spectral distribution, strong emissions in mid-infrared wavelengths, matched rocket exhaust signatures within the algorithm's tolerance bounds. The first alert triggered at 0:15 hours. The duty officer displays at Serpukhov-15 indicated a single launch detection from the central United States. The confidence score was high, above the threshold that required immediate notification to higher command. Petrov received the alert and initiated standard verification procedures. He checked communication links to confirm the data was being received correctly. He examined the alert details, launch location, estimated trajectory, time of detection. The information appeared internally consistent. There were no obvious signs of data corruption or communication failure. The system was reporting what it was designed to report when it detected a launch. Approximately 3 minutes later, additional alerts triggered. The displays now showed 5 separate launch detections, all originating from U.S. ICBM bases, all classified with high confidence. The progression from 1 to 5 detections followed a pattern consistent with either a staged launch sequence or progressive detection of a simultaneous salvo as satellites refined their tracking. From the algorithm's perspective, both explanations were plausible. From the operator's perspective, the situation had escalated from a single anomalous detection to a coordinated pattern suggesting intentional launch activity. The operator displays provided processed information, launch locations marked on a map overlay, confidence scores displayed numerically, estimated impact zones calculated from projected trajectories. What the displays did not show was the raw sensor data underlying these classifications. Petrov could not examine the infrared spectra to assess whether the detected emissions matched rocket exhaust chemistry or exhibited anomalies suggesting alternative sources. He could not review the temporal evolution of sensor voltages to identify whether the signatures showed the characteristic rapid rise and exponential decay of launch plumes or the slower, irregular variations of atmospheric reflections. He could not compare the spatial patterns of detected emissions against known launch site geometries to verify that detections were positioned correctly relative to missile silo locations. The interface provided conclusions. It did not provide evidence. Standard verification procedures required checking for radar confirmation. Ground-based early warning radars positioned along the Soviet periphery were designed to detect incoming missiles after they cleared the horizon and became visible to radar tracking. The temporal sequence of detection was predictable. Satellites would detect launches first, providing 15 to 20 minutes of warning. Radars would confirm detection several minutes later as missiles rose above the radar horizon. At 0:18 hours, radar systems had not yet reported incoming tracks. This was expected. The missiles, if they existed, would not yet be detectable by radar. The absence of radar confirmation was not evidence against the satellite alerts. It was simply an artifact of detection method timing differences. This created an information asymmetry. The satellite system was reporting high-confidence detections based on infrared signatures. Radar systems were reporting no detections based on the absence of radar returns. Both reports were technically accurate. Satellites were detecting infrared emissions. Radars were not detecting ballistic objects. The question was whether the infrared emissions indicated missiles or something else. The operator had no independent means of resolving this ambiguity within the decision timeframe. The protocol required escalating satellite alerts immediately. Waiting for radar confirmation meant accepting delay that could be catastrophic if the alerts were real. Petrov's technical background gave him insight into system behavior that typical duty officers lacked. He understood that the OCO satellites had only recently achieved operational status. He knew that complex systems often exhibit unanticipated behaviors during early operational phases. He was aware that algorithm training is necessarily incomplete, that models learn from finite data sets and may misclassify inputs outside their training envelope. This knowledge was not procedurally relevant. There was no protocol for do not escalate alerts if you suspect the algorithm is encountering edge cases, but it informed Petrov's reasoning as he evaluated the alerts. The strategic implausibility of the detections was the most significant factor in Petrov's assessment. 5 missiles did not constitute a rational first strike. U.S. strategic doctrine, as understood by Soviet intelligence analysts, emphasized overwhelming force in any nuclear exchange. A first strike would aim to destroy Soviet command authority, launch facilities, and strategic forces before they could retaliate. This required hundreds of missiles launched simultaneously from multiple bases to saturate defenses and minimize warning time. 5 missiles could not achieve these objectives. 5 missiles would guarantee Soviet retaliation while failing to meaningfully degrade Soviet retaliatory capability. No rational strategic planner would initiate nuclear war with 5 missiles. This reasoning required Petrov to assert that strategic logic overruled technical data. The satellites were reporting detections. The algorithm was reporting high confidence. Multiple sensors were corroborating each other. The technical evidence said launches had occurred. The strategic reasoning said launches had not occurred because the reported launch pattern made no strategic sense. Resolving this contradiction required choosing which authority to trust: the technical system designed to detect launches, or human judgment about strategic rationality. There was no procedure for making this choice. The system architecture assumed such contradictions would not arise because the algorithm would be reliable. The divergence between system state and operator perception was now complete. The satellites were detecting atmospheric reflections and classifying them as launches. The algorithm was reporting high confidence because the detected signatures matched its training data. The control room displays were showing launch alerts because that is what the system produces when it classifies events as high-confidence threats. Petrov was viewing these alerts and concluding they were probably false because their strategic pattern was implausible. The system believed it was detecting a real attack. The operator believed he was witnessing a false alarm. Both conclusions were logically justified given the information available to each. Both could not be correct. The decision point arrived at approximately 0:20 hours. Petrov had received multiple high-confidence alerts indicating a coordinated launch from the United States. Protocol required immediate escalation to higher command. The alert would propagate through the military chain to political leadership. Strategic forces would be placed on higher alert status. Retaliatory options would be prepared. The process, once initiated, would be difficult to reverse. If the alerts were real, delay meant reduced response options and potential strategic vulnerability. If the alerts were false, escalation meant raising the nuclear alert status of both superpowers based on incorrect information, a scenario with its own catastrophic potential. Petrov chose to report the detections as a probable system malfunction rather than an actual attack. This was not a denial that the system was detecting something. It was an assertion that what the system was detecting was not missiles, despite the system's high confidence that it was detecting missiles. The report to higher command was carefully worded. The satellite system was showing possible launches. Confidence levels were high, but radar confirmation was absent, and the detection pattern was inconsistent with expected attack doctrine. The characterization as system malfunction was procedurally convenient. It explained why high-confidence alerts should not be trusted without requiring Petrov to claim technical knowledge he did not possess about what specifically had malfunctioned. The reality was more complex. Nothing had malfunctioned in the conventional sense. The satellite's infrared sensors were operating within specifications. The telemetry links were functioning correctly. The ground station receivers were processing data without error. The classification algorithm was executing its logic as programmed. Every component of the system was performing its designed function. The malfunction was not in any component, but in the system's premise, the assumption that high-confidence classifications always correspond to the conditions the algorithm was trained to recognize. This premise had failed. The algorithm had encountered environmental conditions outside its training envelope and had produced high-confidence false positives. The system was operating correctly and producing incorrect output, a failure mode the design philosophy had considered implausible. The minutes following Petrov's report were characterized by uncertainty rather than resolution. Higher command acknowledged the report but did not immediately dismiss the alerts. Further verification attempts were initiated. Communications with radar stations continued. The satellite detections persisted for several minutes before gradually ceasing as the orbital geometry changed and the atmospheric conditions producing the reflections moved out of the sensor's fields of view. The pattern of detection cessation, gradual fade-out rather than abrupt termination, was more consistent with changing atmospheric observation conditions than with missile launches whose infrared signatures would persist through powered flight and only terminate at burnout. As time passed without radar confirmation, the probability that the alerts represented false positives increased. Real missiles launched from the central United States would have been detected by Soviet early warning radars within 10 to 12 minutes of launch. At 0:30 hours, 15 minutes after the first alert, no radar contacts had been reported. The absence of radar confirmation after this interval was strong evidence that no missiles existed. The satellite system's certainty had been high. The physical evidence was now contradicting that certainty. The divergence between algorithmic confidence and physical reality was becoming undeniable. The incident exposed a fundamental vulnerability in automated detection systems. High confidence is an internal model property, not a guarantee of external validity. The algorithm reported 95% confidence because the detected signatures matched its training data with 95% fidelity. This statistical claim said nothing about whether the training data comprehensively represented all possible conditions the system would encounter operationally. The model's confidence reflected its internal consistency, not its correspondence to reality. The design premise, that high internal confidence would correlate with high external validity, had failed. The model was confidently wrong. The progression from atmospheric anomaly to near-catastrophic alert escalation followed a chain of causation that was both technically comprehensible and operationally invisible. Each link in the chain represented correct behavior by some component or actor within the system. The satellites detected real infrared emissions. The algorithm classified those emissions according to its programmed logic. The displays presented the classifications accurately. The operator received the information and confronted the decision problem the system architecture had created. The failure was not in any individual element, but in the structure that connected them, a structure built on premises about environmental predictability, algorithmic reliability, and human decision-making that collapsed when tested against operational reality. The physical process generating the false positive signatures involved solar radiation interaction with high-altitude ice crystal clouds under specific geometric conditions. Sunlight in the infrared spectrum, wavelengths between 1 and 5 micrometers, penetrates the atmosphere with relatively little absorption. When this infrared radiation strikes ice crystals at particular angles, several optical phenomena occur simultaneously. Specular reflection from crystal faces redirects the radiation without wavelength shift. Internal refraction within hexagonal ice crystal structures can concentrate radiation through geometric focusing effects. Multiple scattering between adjacent crystals can produce complex spatial intensity patterns. The net result, under specific combinations of solar angle, cloud altitude, crystal orientation distribution, and observer viewing geometry, is localized regions of enhanced infrared intensity that can exceed background levels by orders of magnitude. The OCO satellite's infrared sensors, operated in spectral bands selected to maximize sensitivity to rocket exhaust emissions while minimizing interference from solar and terrestrial thermal background. The specific bands, centered around 2.7 micrometers and 4.3 micrometers, corresponded to strong emission lines from carbon dioxide and water vapor in rocket exhaust plumes. These same wavelengths are present in reflected sunlight. The sensors could not distinguish emitted infrared from reflected infrared based on wavelength alone. The distinction required analysis of temporal evolution, spatial patterns, and spectral distributions, precisely the analysis the classification algorithm was designed to perform. The algorithm's training data had included various atmospheric conditions, clear skies, low clouds, high clouds, day and night observations, seasonal variations. What the training data had not included, because the conditions had not been identified during testing, was the specific configuration of cloud altitude, ice crystal structure, solar angle, and orbital viewing geometry that produced reflection patterns matching launch signatures. This was not a testing oversight in the conventional sense. The space of possible atmospheric configurations is effectively infinite. Testing cannot exhaustively sample infinite parameter spaces. Testing samples conditions deemed representative. The premise that representative sampling ensures reliability requires that operational conditions cluster tightly around tested conditions. Atmospheric physics does not guarantee this clustering. Edge cases exist. Given sufficient operational time, edge cases will be encountered. When the satellites detected the enhanced infrared emissions from cloud reflections, the raw sensor data voltage signals proportional to infrared intensity at each spectral band exhibited characteristics similar to early-phase rocket plumes. The intensity was high relative to background. The spectral ratio between the 2.7 and 4.3 micrometer bands matched the expected ratio from hydrocarbon combustion. The spatial extent was concentrated several kilometers across, consistent with a plume that had not yet dispersed significantly. The temporal evolution showed increasing intensity over several seconds as the viewing geometry changed slightly with orbital motion, creating the appearance of a plume brightening during powered ascent. The algorithm processed this data through a decision tree trained on known launch examples and known non-launch examples. At each decision node, the algorithm compared observed signal characteristics against threshold values learned during training. Intensity above threshold, consistent with launch. Spectral ratio within range, consistent with launch. Spatial concentration within bounds, consistent with launch. Temporal rate of change within expected range, consistent with launch. The accumulated decision path led to a classification: launch detected, confidence 0.94. The algorithm had no mechanism to recognize that it was operating outside its training envelope. Pattern matching algorithms cannot detect their own limitations. They classify all inputs according to learned patterns, even when inputs differ fundamentally from training data. The confidence score 0.94 or 94% reflected the algorithm's internal consistency, not its external accuracy. The score indicated that 94% of training examples with similar signal characteristics had been actual launches. This was a conditional probability, given that the signal matches these patterns, and given that the training data accurately represents operational conditions. The probability of an actual launch is 94%. Both conditions were critical. The signal did match the patterns. The training data did not accurately represent this operational condition. The confidence score was statistically valid within the model's framework and operationally misleading in the real environment. The control room displays at Serpukhov-15 translated these classifications into operational alerts. The interface showed launch locations marked on a geographic display, confidence scores presented numerically, projected impact zones calculated from estimated trajectories, and timestamps indicating when each detection occurred. The presentation was designed for rapid comprehension. It succeeded in conveying the algorithm's conclusions clearly. It failed to convey the uncertainty inherent in those conclusions. The numerical confidence score 0.94 suggested precision. It implied that the model had quantified its uncertainty and found it acceptably low. This interpretation was incorrect. The confidence score quantified training data consistency. It said nothing about whether the current operational scenario resembled the training data or represented a novel condition the model had never encountered. The progression from 1 detection to 5 detections followed the satellite's orbital motion and the spatial extent of the atmospheric conditions producing the false signatures. As the first satellite's field of view swept across the reflective cloud region, the algorithm detected what it classified as a single launch. As the satellite's motion brought additional portions of the cloud field into view, or as other satellites in the constellation independently observed the same atmospheric region from different angles, additional detections triggered. From the algorithm's perspective, this progression was consistent with either a staged launch sequence or progressive detection of a multi-missile salvo. From a physics perspective, it was the natural consequence of orbital motion revealing different portions of a spatially extended atmospheric phenomenon. Petrov's assessment that 5 missiles made no strategic sense was based on knowledge external to the detection system. Soviet intelligence had extensive analyses of U.S. strategic doctrine, force structure, and likely attack patterns. A first strike would aim to neutralize Soviet retaliatory capability through massive simultaneous attacks on command centers, ICBM fields, bomber bases, and submarine pens. This required coordinated launches of several hundred missiles to ensure coverage of all targets and to overwhelm defensive systems. Launching 5 missiles achieved none of these objectives. It would alert Soviet defenses without degrading Soviet response capability. It would guarantee retaliation without achieving strategic advantage. From a game-theoretic perspective, it was dominated by all other options. It made no sense. This reasoning was not algorithmic. It could not be encoded in a pattern-matching classifier trained on infrared sensor data. It required understanding adversary intentions, strategic calculations, and military doctrine. These were human analytical domains. The OCO system was not designed to perform strategic assessment, it was designed to detect launches. The implicit assumption was that strategic assessment would occur at higher command levels after detection. The problem was that the decision architecture required immediate escalation of high-confidence detections, leaving minimal time for strategic assessment before alerts propagated through the command chain and triggered response preparations. The decision trap Petrov faced was structural. If he escalated the alert as protocol required, he would initiate processes designed to culminate in potential nuclear retaliation. These processes were not easily reversible. Once strategic forces were placed on high alert, once political leadership was informed of possible attack, once retaliatory options were prepared, the momentum toward action became substantial. The system was designed for rapid response, not for careful deliberation. If the alerts were real, this design was essential. If the alerts were false, this design was catastrophic. Petrov had no definitive way to determine which case applied. If he did not escalate the alert, he violated protocol based solely on strategic reasoning that might be wrong. Perhaps U.S. doctrine had changed. Perhaps the detected launches were a probe to test Soviet response times. Perhaps they were a limited strike intended to destroy a specific high-value target. Perhaps they were the first wave of a larger attack whose remaining missiles had not yet been detected. All of these scenarios were implausible, but none were impossible. Petrov's assessment that 5 missiles made no strategic sense was a probabilistic judgment, not a certainty. He was betting that his strategic reasoning was correct, and that the satellite system's technical data was wrong. If he was wrong, his failure to escalate would delay Soviet response and potentially compromise retaliatory capability. The operational timeframe compressed this decision problem into minutes. At 0:15, the first alert arrived. By 0:20, 5 alerts had triggered. Petrov had perhaps 10 minutes to assess the situation, make a decision, and communicate that decision to higher command, before the expected timeline for radar confirmation would pass. 10 minutes is insufficient for detailed technical analysis of sensor data, for consultation with system engineers, for independent verification through alternative intelligence sources, for deliberative strategic assessment. 10 minutes is barely sufficient to execute standard alert procedures. The time pressure was not accidental. It was designed into the system specifically to ensure rapid response. The design premise was that rapid response to real threats was more important than careful verification of ambiguous data. This premise optimized for false negative avoidance at the cost of false positive susceptibility. The feedback loop between operator belief and system state was unidirectional. Petrov's assessment that the alerts were false did not alter the satellite detections. The algorithm continued reporting high confidence. The displays continued showing launch alerts. The system's behavior was independent of the operator's judgment. This unidirectionality was deliberate. Allowing operators to modify system output based on subjective assessment would undermine the objectivity and consistency that automation was meant to provide. But unidirectionality also meant that operator skepticism could not feed back into the detection process to trigger additional verification, alternative analysis, or confidence recalibration. The system and the operator existed in parallel universes of interpretation with no mechanism for reconciliation except through external validation that required more time than the decision architecture allowed. The physical impossibility of the alerts becoming clear within the decision time frame was a direct consequence of the verification methods available. Radar confirmation required missiles to rise above the radar horizon, which required several additional minutes beyond satellite detection. Optical tracking from ground-based telescopes required clear weather, darkness, and precise pointing, none reliably available on short notice. Communications intelligence could potentially detect launch preparation activities at U.S. missile bases, but such detection was not real-time and would not confirm or refute sudden launches. The only verification method operating on a timescale comparable to the decision requirement was strategic reasoning. Does the reported attack pattern make sense given known adversary doctrine? This method was fast but subjective, unreliable, and not formally part of the alert protocols. Petrov's decision to report a probable system malfunction was, in effect, a decision to trust human strategic reasoning over algorithmic pattern matching when the two contradicted each other. This was not a decision the system architecture anticipated operators making. The design philosophy positioned algorithms as authoritative and operators as executors. Petrov inverted this hierarchy. He asserted that his judgment about strategic plausibility was more reliable than the satellite system's judgment about infrared signature classification. He was correct, but he could not prove his correctness within the decision timeframe. His correctness was only confirmed retrospectively, after sufficient time passed without radar confirmation, to make the absence of missiles undeniable. The failure chain's completion did not require any component to malfunction. The satellites detected real signals. The algorithm classified correctly according to its training. The displays presented accurately. The operator received reliable information about what the system believed. Each element performed its function. The chain failed because the functions, when combined, produced a system-level behavior high-confidence false positive escalation that no individual component was designed to prevent. The failure was emergent. It arose from the interaction of correct local behaviors producing incorrect global outcomes. This is the characteristic signature of systems failure. Not component breakdown, but architectural inadequacy revealed under operational stress. The point of no return, had Petrov escalated the alert, would not have been clearly defined. There was no single moment at which escalation became irreversible. Rather, there would have been a progressive loss of flexibility as alert protocols activated successive response stages. Higher command would be informed. Strategic forces would increase readiness. Political leadership would be briefed. Retaliatory options would be prepared. Each stage would take time to execute and time to reverse. The cumulative momentum would make de-escalation increasingly difficult even as the lack of radar confirmation made the false positive increasingly apparent. The system was designed to accelerate toward action, not to facilitate reconsideration. This asymmetry between escalation and de-escalation was intentional, a design choice prioritizing rapid response capability over error correction capability. The immediate aftermath of Petrov's decision not to escalate the satellite alerts as an actual attack introduced a different category of operational challenge: how to interpret and respond to a system that had generated high-confidence false positives without clear technical explanation. The satellites had detected real infrared emissions. The algorithm had classified those emissions as launches according to its programmed logic. The control room displays had presented the classifications accurately. Yet no missiles existed. The system had been simultaneously correct in reporting what its sensors detected and wrong in concluding what those detections represented. This duality created interpretive ambiguity that would shape institutional response and future operational doctrine. The period between 0:20, when Petrov reported probable system malfunction, and 0:35, when the absence of radar confirmation became definitive, was characterized by sustained uncertainty rather than immediate resolution. Higher command acknowledged Petrov's report but maintained heightened alert posture pending verification. Additional radar stations were queried. Communications channels to other intelligence sources were activated. The satellite system continued operating, and the detections gradually faded as the orbital geometry changed and the atmospheric conditions producing the false signatures moved out of the sensor's fields of view. This fade-out pattern, progressive weakening rather than abrupt termination, provided indirect evidence against the launch hypothesis. Real missile plumes would maintain infrared visibility through powered flight lasting several minutes. The observed detections ceased sooner and more gradually than rocket exhaust would permit. By 0:40, the absence of radar confirmation had become statistically conclusive. Ballistic missiles launched from central U.S. locations would have been detectable by Soviet early warning radars positioned along the northern and eastern periphery within 12 to 15 minutes of launch. The temporal window had passed. No radar contacts had been reported. The satellite alerts had not been confirmed by independent sensors. The probability that the alerts represented actual launches had fallen below any reasonable threshold for sustained alert posture. The immediate crisis had been averted. What remained was the more complex problem of understanding why the crisis had occurred. The diagnostic challenge centered on determining what had gone wrong. In traditional hardware failures, the path to diagnosis is relatively straightforward. Identify the malfunctioning component, examine its physical state, determine the failure mechanism, implement, repair or replacement. In software failures, diagnosis follows similar logic. Identify the erroneous code, trace the execution path that produced incorrect output, correct the logical error, verify the correction through testing. The Serpukhov-15 incident fit neither pattern. The hardware had not malfunctioned, the sensors had detected real infrared emissions. The software had not contained a bug. The algorithm had executed its classification logic correctly. The failure resided not in any component, but in the model's incompleteness. This created a diagnostic paradox. If asked what failed, the accurate answer was nothing. If asked why did the system report launches when no launches occurred, the accurate answer was because atmospheric conditions produced infrared signatures indistinguishable from launches within the algorithm's classification framework. This answer was technically correct, but operationally unsatisfying. It implied that the system could generate false positives whenever sufficiently rare atmospheric conditions occurred. It suggested that high-confidence detections could not be trusted unconditionally. It undermined the premise that validated systems are reliable systems. These implications were institutionally uncomfortable. Institutional response to the incident reflected this discomfort. Initial internal reports characterized the event as a system malfunction, aligning with Petrov's real-time assessment. This characterization was convenient. It located the failure in the technical system rather than in human decision-making or strategic doctrine. It suggested a correctable problem: fix the malfunction, restore reliability, continue operations. The characterization was also misleading. There was no discrete malfunction to fix. The system had operated according to its design. The design itself had proven inadequate when confronted with conditions outside its validation envelope. Subsequent technical investigation attempted to reconstruct the physical conditions that had produced the false detections. Satellite telemetry logs were reviewed. Sensor data from the incident period were analyzed. Atmospheric conditions were reconstructed from meteorological records and orbital position data. The investigation determined that high-altitude cloud formations over the Pacific, combined with specific solar angles and satellite viewing geometry, had produced infrared reflections that matched the algorithm's launch classification criteria. This explanation was plausible and consistent with available data. It did not lead to obvious corrective actions. The fundamental problem was that atmospheric conditions producing false positives were rare but not impossible, unpredictable but not preventable, identifiable in retrospect but not recognizable in real time. The OCO system could not be redesigned to eliminate this failure mode without fundamentally altering its detection sensitivity. Increasing the confidence threshold to avoid false positives would increase the risk of misdetections, false negatives. Modifying the classification algorithm to reject ambiguous signatures more aggressively would require training data representing the problematic atmospheric conditions. But those conditions had only been identified because they produced a false positive. The data needed to prevent future false positives did not exist until after false positives occurred, creating a circular dependency that made proactive correction impossible. Operator training was updated to include awareness that high-confidence satellite alerts could, under rare circumstances, represent false positives. Duty officers were instructed to consider strategic plausibility when evaluating alerts and to report detections with appropriate caveats when radar confirmation was not immediately available. These training modifications were modest. They did not alter the fundamental decision architecture. Operators still received processed classifications rather than raw data. Time pressure still constrained verification opportunities. Procedural requirements still emphasized rapid escalation. The structural conditions that had created Petrov's decision trap remained largely unchanged. The incident's broader implications for nuclear command and control doctrine were not immediately addressed. The false positive had been contained by individual operator judgment exercised in defiance of procedure and system authority. This was not a reproducible safety mechanism. It depended on the specific operator possessing technical knowledge, strategic awareness, and psychological independence sufficient to question automated output. Future incidents might involve different operators lacking these qualities. Future false positives might occur under different geopolitical conditions where strategic plausibility assessment was more ambiguous. The incident had revealed a vulnerability, but had not prompted systematic architectural redesign to address that vulnerability at its source. The secondary crisis was conceptual rather than operational: how to maintain confidence in early warning systems after those systems had demonstrated fundamental limitations. The Oko constellation remained the Soviet Union's primary space-based detection capability. No alternative system with comparable performance existed. The choice was not between a reliable system and an unreliable one, but between an imperfectly reliable system and no system at all. The rational response was to continue operations while acknowledging limitations. The institutional tendency was to minimize discussion of limitations to preserve system credibility and operator confidence. This tendency created information asymmetry within the military hierarchy. Senior leadership and strategic planners needed accurate understanding of system reliability to inform doctrine and response planning. Operational personnel needed confidence in their tools to perform effectively under stress. These needs were in tension. Emphasizing system limitations could undermine confidence. Understating limitations could lead to over-reliance on imperfect detection. The balance was difficult to calibrate and varied across organizational levels and timescales. Petrov's role in the incident was officially acknowledged but not publicly celebrated. He received limited recognition within military channels and faced some criticism for not following escalation protocols precisely as written. The ambiguity of his status reflected the ambiguity of his decision. He had been correct in concluding the alerts were false. He had been procedurally incorrect in not escalating them immediately. His correctness was validated only retrospectively, after time confirmed the absence of missiles. At the moment of decision, he had violated protocol based on judgment that was reasonable but not provable. The institutional response to such violations is inherently conflicted. They represent both valuable independent thinking and dangerous precedent. The incident remained classified for years. Public disclosure did not occur until after the Cold War ended, and Petrov was no longer in active service. The secrecy was partly operational. Acknowledging false positives could undermine adversary perceptions of Soviet detection capability, and partly institutional. Acknowledging system limitations was professionally and politically uncomfortable. The delay in disclosure meant that lessons from the incident were not widely disseminated within the international strategic community during the period when they were most relevant. Other nations operating similar systems did not benefit from Soviet experience with detection model limitations. The broader pattern of false alarms in nuclear early warning systems during the Cold War period only became clear in retrospect. The U.S. NORAD system had experienced false positives in 1979 when a training tape was mistakenly inserted into operational computers, and in 1980 when a faulty integrated circuit chip produced false missile count displays. The Soviet Oko system generated the September 1983 false positive. Each incident was unique in its specific technical cause, but shared common characteristics: high confidence false information from authoritative systems, compressed decision timeframes, potential for catastrophic escalation based on incorrect data. The pattern suggested systematic vulnerability rather than isolated malfunctions. This pattern indicated a fundamental tension in early warning system design. The systems were intended to provide rapid, reliable detection of missile launches to maximize decision time for response. Reliability required comprehensive validation and testing, but validation could not exhaustively cover all possible environmental conditions, technical failure modes, and operational scenarios. The systems were necessarily incomplete. Their incompleteness manifested as occasional false positives and potential false negatives. Managing this incompleteness required human judgment, operating under time pressure, with incomplete information, precisely the condition the automation was meant to eliminate. The strategic stability implications were profound. Mutual assured destruction as a deterrence doctrine depended on credible second strike capability. Second strike capability required reliable warning of first strike to enable launch on warning or launch under attack options. But if warning systems could generate high-confidence false positives, then launch on warning became launch on possible false alarm. The doctrine assumed detection reliability that the technology could not guarantee. This assumption created permanent risk of accidental escalation. The risk could be reduced by increasing decision time and verification requirements, but doing so reduced responsiveness to real attacks. The trade-off was irreducible given existing technology and strategic geometry. Petrov's decision had prevented one path to potential nuclear escalation. It did not eliminate the vulnerability that had created that path. The OCO system continued operating with the same architectural characteristics that had produced the false positive. The decision protocols continued requiring rapid escalation of high-confidence alerts. The geopolitical tensions that made strategic plausibility assessment difficult continued to shape the operational environment. The conditions that had made the incident possible remained in place. What had changed was historical luck, the specific combination of atmospheric conditions, orbital geometry, and individual operator judgment that had converged on September 26, 1983, had produced a near miss rather than a catastrophe. But luck is not a safety strategy. The incident's resolution was, in this sense, incomplete. The immediate crisis had been averted. The system-level vulnerability had been identified, but the structural factors producing that vulnerability had not been eliminated. They could not be eliminated without fundamental redesign of early warning architectures, decision timelines, and verification procedures changes that would require international coordination, political will, and acceptance of reduced responsiveness as the price of increased reliability. These changes did not occur. The systems continued operating. The vulnerability persisted. The full significance of the September 26, 1983 incident only became clear through accumulated historical perspective and comparative analysis of similar events across different early warning systems. What appeared at the time as an isolated technical anomaly, a rare false positive from a newly operational satellite constellation, revealed itself as an instance of a systematic failure class inherent to pattern recognition systems operating under incomplete environmental knowledge. The incident was not unique. It was representative. The forensic reconstruction that followed the incident identified the specific atmospheric and geometric conditions producing the false infrared signatures. But this identification was retrospective rather than predictive. The combination of high-altitude cirrus clouds, solar illumination angle, ice crystal orientation distribution, and satellite viewing geometry that had generated launch-like reflections could be explained after the fact using established atmospheric optics principles. The same combination could not have been anticipated before occurrence because the parameter space of possible atmospheric configurations exceeded the boundary of tested conditions by orders of magnitude. The model's training data had sampled atmospheric variability. It had not exhaustively enumerated atmospheric possibility. This distinction between sampling and enumeration is fundamental to understanding why validation testing cannot guarantee operational reliability in pattern recognition systems. Testing validates that a model performs correctly on tested inputs. It cannot validate that tested inputs comprehensively represent the operational input space. When the operational space is continuous and effectively infinite, as atmospheric conditions are, comprehensive testing is mathematically impossible. The premise that representative sampling ensures reliability requires that operational conditions cluster tightly around tested conditions with rare excursions beyond test boundaries. This clustering is an empirical claim, not a logical necessity. It must be verified through operational experience. The September 26 incident provided that verification. The clustering assumption was incorrect. Statistical analysis of early warning system performance across multiple nations and decades revealed that false positives were not rare anomalies, but recurring features of operational experience. The U.S. NORAD system had experienced a major false alarm on November 9, 1979, when a training scenario tape depicting a large-scale Soviet attack was mistakenly loaded into the operational alert computer at NORAD headquarters in Cheyenne Mountain. The system processed the scenario data as real telemetry and generated alerts indicating 250 Soviet submarine-launched ballistic missiles approaching North American targets. Fighter aircraft were launched. The National Emergency Airborne Command Post, the so-called Doomsday Plane, was readied for takeoff. Minuteman missile crews were placed on high alert. The error was identified within 6 minutes when satellite systems reported no detections and radar systems showed no inbound tracks. The false positive had been produced not by algorithmic misclassification, but by operational procedure failure. The wrong data had entered the system. 6 months later, on June 3, 1980, NORAD systems again generated false alerts, this time reporting 220 incoming Soviet ICBMs. The alert was brief, less than 3 minutes before being recognized as false but triggered similar response protocols. The cause was traced to a faulty integrated circuit chip in a communications processor that was generating random data patterns resembling missile count codes. The failure was hardware-based but architecturally similar to the OCO incident. The system received data matching threat signatures and classified that data as representing actual threats because no mechanism existed to verify that the data reflected physical reality rather than technical artifact. These incidents, together with the September 1983 OCO false positive, defined a pattern. Early warning systems operating under time pressure with incomplete verification procedures would occasionally generate high-confidence false alerts. The specific causes varied: atmospheric anomalies, procedural errors, hardware faults, but the operational consequence was consistent. Authoritative systems reported threats that did not exist. The decision architectures surrounding these systems were optimized for rapid response, not for careful verification. The result was that false positives propagated through command chains and triggered alert protocols before their falsity could be established. The frequency of such incidents was low but non-zero. Exact statistics remained classified, but available evidence suggested false alarm rates on the order of several events per decade across U.S. and Soviet systems combined. This rate was low enough that individual operators might complete entire careers without experiencing a false positive. It was high enough that false positives were operationally certain over system lifetimes measured in decades. The question was not whether false positives would occur, but when, and whether human judgment would successfully contain them when they did occur. The mathematical inevitability of false positives in pattern recognition systems is well established. In statistical decision theory, any classification system operates by partitioning input space into regions corresponding to different classes. The partition boundaries are determined by training data and by design choices about acceptable trade-offs between false positive and false negative errors. No partition is perfect. Some inputs near decision boundaries will be misclassified. The misclassification rate depends on the true distribution of inputs relative to the learned partition. When the true input distribution extends beyond the training data distribution, as operational environments inevitably do, misclassification rates for novel inputs cannot be reliably predicted from training performance. For the OKO system, this meant that performance on tested atmospheric conditions did not guarantee performance on untested conditions. The algorithm had learned to recognize launches under tested conditions with high accuracy. It had not learned, could not have learned, to recognize all possible non-launch conditions that might produce similar sensor signatures. The asymmetry is fundamental. Learning to recognize a target class requires positive examples of that class. Learning to reliably reject all non-target inputs requires comprehensive sampling of the complement space. For finite target classes and infinite complement spaces, comprehensive sampling is impossible. This mathematical reality has direct operational implications. Early warning systems cannot be made perfectly reliable through better training, more testing, or algorithmic sophistication. They can be made more reliable by accepting lower sensitivity, higher detection thresholds that reduce false positives at the cost of increased false negatives. But this trade-off is not free. In strategic contexts, where false negatives mean missed detection of actual attacks, accepting reduced sensitivity means accepting increased strategic vulnerability. The optimization problem has no ideal solution. Any chosen operating point represents a compromise between competing risks. The human factors dimension of the Serpukhov-15 incident became central to subsequent analyses of command and control system design. Petrov's decision to question high-confidence algorithmic output rather than escalate immediately had prevented the incident from propagating beyond the initial alert stage. This intervention was valuable. It was also unreliable as a systematic safety mechanism. Petrov had possessed specific characteristics: technical knowledge of system design, strategic awareness enabling plausibility assessment, psychological independence enabling procedural deviation, that were not guaranteed in arbitrary operators. Future false positives might be evaluated by personnel lacking these characteristics. Future incidents might occur under geopolitical conditions where strategic plausibility was more ambiguous. Relying on individual operator judgment as the primary barrier to false positive escalation was organizationally fragile. This recognition prompted gradual evolution in early warning doctrine and training. Operator authority to question system outputs was formally acknowledged and, in some contexts, explicitly encouraged. Training scenarios began including false alarm cases to familiarize operators with the possibility that high-confidence alerts could be wrong. Procedural modifications introduced verification steps and decision delays designed to create opportunities for independent assessment before irreversible escalation. These changes were incremental and incomplete. They reflected institutional learning, but did not fundamentally redesign the decision architectures that created time pressure and information asymmetry. The broader strategic implications concerned the viability of launch-on-warning doctrines in the presence of false positive risk. Launch-on-warning, the policy of authorizing nuclear retaliation based on warning of incoming attack before actual detonations occur, was adopted by both the United States and Soviet Union to ensure second strike capability even if leadership and control systems were targeted in a first strike. The doctrine required credible warning with sufficient lead time to enable launch decisions. Early warning satellites and radars provided that capability. But if those systems could generate false positives, then launch-on-warning became launch-on-possible error. The probability of false positive-induced nuclear war was not calculable with precision. It depended on false alarm rates, operator decision-making under stress, verification procedure effectiveness, geopolitical context influencing plausibility assessment, and numerous other factors with uncertain distributions. What could be stated with confidence was that the probability was non-zero, and would remain non-zero as long as rapid response doctrines depended on automated detection systems operating under environmental uncertainty. The risk could be reduced through improved technology, better training, and enhanced verification procedures. It could not be eliminated without either accepting longer decision timelines, which degraded second strike assurance, or abandoning launch-on-warning entirely in favor of launch-after-attack doctrines that accepted greater vulnerability to first strike damage. The Serpukhov-15 incident became publicly known only in 1998, 15 years after occurrence, when Petrov's role was disclosed in post-Cold War historical accounts. The revelation attracted significant attention in strategic studies and arms control communities. Retrospective analysis emphasized how close the incident had brought the world to potential nuclear escalation. Popular accounts framed Petrov as the man who saved the world. These framings were dramatically compelling, but analytically imprecise. Petrov had made a correct decision under uncertainty. His decision had prevented a false positive from escalating. It had not saved the world in any singular sense because the path from false positive to actual nuclear exchange was neither direct nor certain. Multiple additional decision points and verification stages existed between satellite alert and weapon release. The more precise lesson was that individual human judgment, exercised at the right moment by a person with appropriate knowledge and independence, could interrupt automated escalation chains when systems generated false outputs. This was valuable but insufficient. Safety architectures that depend on exceptional individuals making correct decisions at critical moments are not robust. They are vulnerable to personnel variability, to organizational pressures that discourage independent judgment, to stress and time pressure degrading cognitive performance. Reliable safety requires systematic barriers to catastrophic error redundancy, verification, decision delays, reversibility, not dependence on individual heroism. The incident also illustrated the fundamental tension between automation and judgment in high-stakes decision systems. Automation was introduced to eliminate human error to provide consistent, objective, rapid threat assessment unaffected by stress, fatigue, or cognitive bias. The OKO system succeeded in these goals. It provided rapid, consistent classification of infrared signatures according to programmed logic. It eliminated the variability and delay inherent in human interpretation of raw sensor data. In doing so, it also eliminated the human capacity to recognize that algorithmic certainty does not equal truth, that high confidence based on pattern matching does not guarantee correspondence to reality, that strategic implausibility should outweigh technical authority. This elimination was not accidental. It was the intended function of automation, to constrain human discretion precisely because human judgment was viewed as unreliable. The paradox was that the system's safety ultimately depended on human judgment, specifically on judgment capable of recognizing when to distrust automation. The design philosophy had attempted to remove judgment from the process. The operational reality was that judgment remained essential, but had been displaced to less favorable conditions, compressed timeframes, limited information, procedural constraints, institutional pressure against questioning authoritative systems. The systemic lesson extended beyond nuclear command and control to all high-stakes automated decision systems operating under uncertainty. Medical diagnostic systems, financial risk models, autonomous vehicle perception systems, content moderation algorithms all share common architectural characteristics with early warning systems. They employ pattern recognition to classify inputs into categories with significant consequences. They operate under time or resource constraints that limit verification. They are trained on finite data and deployed in environments containing conditions not represented in training. They report confidence scores that quantify internal consistency rather than external validity. They are embedded in organizational and technical architectures that shape how their outputs are interpreted and acted upon. For all such systems, the Serpukhov-15 incident provides a canonical failure example. The failure was not dramatic equipment breakdown or obvious design error. It was subtle model limitation revealing itself under edge case conditions. The model had been properly trained, thoroughly tested, and correctly implemented. It had been validated according to standard engineering practice. It failed because standard engineering practice could not anticipate all operational conditions, and because high performance on tested cases does not guarantee reliable performance on untested cases when the operational environment contains effectively infinite variability. The design premise that had failed was the assumption of environmental predictability, that operational conditions would be sufficiently similar to test conditions that validated models would generalize reliably. This premise is commonly implicit in engineering practice. It is often correct for systems operating in controlled environments with low variability. It is systematically unreliable for systems operating in natural environments: atmosphere, ocean, space, human behavior, where variability is high and novel conditions emerge continuously. For such systems, the question is not whether models will encounter inputs outside their training envelope, but when. Recognition of this inevitability requires different design philosophy. Rather than attempting to build perfectly reliable detection through comprehensive training and testing, an impossible goal, the approach should emphasize robustness to model uncertainty. This includes explicit confidence calibration that distinguishes internal pattern matching consistency from external validity, architectural provisions for verification and human oversight operating on appropriate timescales, decision procedures that prevent irreversible actions based on single sources of ambiguous data, and organizational culture that legitimizes questioning automated authority when outputs conflict with domain knowledge or strategic context. These principles were partially incorporated into subsequent early warning system designs and operational doctrines. The incorporation was incomplete and politically constrained. Strategic stability considerations limited the extent to which nations were willing to lengthen decision timelines or reduce launch readiness. International cooperation that might have enabled shared understanding of detection system limitations was inhibited by classification and strategic competition. The improvements that did occur: better operator training, more sophisticated algorithms, additional verification sensors reduced false positive risk, but did not eliminate the fundamental vulnerability. The Serpukhov-15 incident stands as a demonstration that high-stakes automated systems will occasionally fail in ways that are predictable in principle but unpreventable in practice. The atmospheric conditions producing the false positive were physically understood and technically explainable after occurrence. They were not anticipated before occurrence because the space of possible conditions exceeded the space of tested conditions. The algorithm's response classifying the signatures as launches with high confidence was correct according to its training. The training was incomplete relative to operational reality. The incompleteness was inevitable given finite test resources and infinite environmental variability. The answer to the question posed at the beginning returns with clarity. A validated model can produce operationally certain output while being structurally incapable of distinguishing the scenario it was designed to detect because validation tests known conditions while operations encounter unknown conditions. The model's confidence reflects its internal consistency, not its external accuracy. When operational inputs fall outside the training distribution, high confidence becomes a measure of the model's inability to recognize its own limitations, rather than a measure of correctness. This is not a flaw specific to the OCO satellite system. It is a fundamental characteristic of inductive inference applied to open-world problems. Models learn from finite examples. Operational environments generate infinite variety. The gap between finite training and infinite operation is where failures emerge. These failures are not engineering errors that better design could prevent. They are epistemological limits that no amount of engineering can eliminate. What engineering can do, and what the Serpukhov-15 incident starkly illustrated was necessary, is to design systems that remain safe when models fail, rather than systems that assume models will not fail. The incident's historical importance lies not in its dramatic potential, the catastrophe that did not occur, but in its analytical clarity. It demonstrated, in a context where consequences could not have been more severe, that automation creates new failure modes even as it eliminates old ones. It showed that confidence is not certainty, that validation is not proof, that reliability is context-dependent, and that human judgment remains essential precisely where it is most difficult to exercise effectively. These lessons apply wherever pattern recognition systems make consequential classifications under uncertainty. The atmospheric physics of September 26, 1983 were specific to early warning satellites. The failure architecture was universal. The final observation concerns what was not learned. Despite the incident's clear demonstration of systemic vulnerability, and despite similar false alarms in other systems confirming the pattern, fundamental redesign of early warning architectures did not occur during the remaining Cold War years. Launch-on-warning doctrines persisted. Rapid response requirements continued to compress decision timelines. Verification procedures remained limited by physics and geography. The systems continued operating with known vulnerabilities because the alternative's longer decision times, reduced launch readiness, acceptance of greater first-strike vulnerability, were strategically unacceptable to national leadership. This gap between demonstrated risk and implemented change reflects a persistent tension in safety-critical systems. The knowledge that current designs are inadequate does not automatically generate superior alternatives when operational requirements are inflexible and technological constraints are fundamental. The Serpukhov-15 incident proved that early warning systems were structurally vulnerable to false positive-induced escalation. It did not prove how to build early warning systems that provided equivalent strategic warning capability without that vulnerability. The lesson was learned. The problem remained unsolved. Stanislav Petrov's decision on September 26, 1983, prevented one instance of false positive escalation. It did not prevent the next atmospheric edge case, the next hardware fault, the next procedural error. Those would occur, as statistical inevitability demanded, when sufficient operational time accumulated. Whether they would be contained depended on whether future operators possessed the judgment, knowledge, and independence that Petrov had demonstrated. Whether the world would be fortunate enough to have such operators on duty at the critical moments was not a question engineering could answer. It was a question of luck, and luck, as the incident made undeniably clear, is not a foundation for strategic stability. The system had not failed because humans were careless or technology was primitive. It had failed because the information structure and embedded assumptions made wrong decisions plausible, procedurally required, and institutionally difficult to question. The instruments reported truth. The truth was insufficient to diagnose reality. The model was validated. The validation could not guarantee operational correspondence. The operators were trained. The training optimized for the wrong scenario. The architecture was designed. The design created the vulnerability it was meant to eliminate. This was not a story of things going wrong. It was an anatomy of how things could appear completely right while being fundamentally wrong, how correct components could combine into incorrect systems, how high confidence could mask deep uncertainty, how designed safety could create emergent danger. The satellites saw what they were designed to see. The algorithm classified what it was trained to classify. The operators did what they were trained to do, until one operator, at one critical moment, did what no one had been trained to do: trust human reasoning over algorithmic authority when the two contradicted each other without either being provably wrong. That this trust was correct was discovered only afterward. That it was necessary was proven by the consequences of its absence. That it was insufficient as a safety strategy was evident from its dependence on circumstances that could not be engineered or guaranteed. The incident revealed the premise of the model as wrong, not in its technical implementation, but in its foundational assumption that pattern matching trained on finite examples could reliably classify infinite operational variety with sufficient confidence to justify rapid, irreversible, existentially consequential action. When the premise is wrong, no amount of correct execution can produce correct outcomes. The OCO system executed correctly. The premise failed. The failure was structural, inevitable, and revelatory of fundamental limits in how automated certainty relates to operational truth. This was the lesson of Serpukhov-15. Not that one system failed once, but that all such systems will eventually encounter the edge of their training envelope, and when they do, their confidence will remain high even as their validity collapses. The only question is whether human judgment, operating under the worst possible conditions, will recognize the divergence before irreversible decisions are made. On September 26, 1983, that recognition occurred. The next time, it might not. The system continues operating. The vulnerability remains. The premise is still wrong.